All right, so the point of section 12.4, the title of the section is, I'm going to just call it curves / definitions. The book has a slightly different name of the chapter, but basically the idea of this section is to nail down a few definitions associated to curves and parameterizations of curves, and even what those two terms mean, just as we move ahead in the course. So I'll sort of subdivide this into a few sections and we'll just go through these. So we'll start by saying curves versus parameterizations. So let me start by sort of giving an example of a vector valued function. So consider the VVF. We'll do a simple one that we know, because this isn't really supposed to be a lesson in vector value functions. So cosine t I plus sine t j for t between 0 and 2 pi. And so the picture of this is one of the first ones we drew. Very simple circle. Radius 1, centered at the origin. Starts here, goes in counterclockwise direction. So there are two terms I want to introduce here. So the first one is a curve. The curve, what we mean by the phrase the curve, is the picture, is the graph of the vector valued function, not the vector valued function itself. And we'll see the difference in a second, is that this is really the picture. It's spelled badly. The picture / graph. So that's, let me use some colors here. That's this thing right here. That's a curve. I could have drawn that even without a vector valued function. Could have just drawn a circle. And 2 is what's called a parametrization. Of a curve. That's the vector valued function. So in that case, we're referring to this thing right here. So the point I want to make to begin with is just to make sure, well, two things. One is to make sure that we're clear on the difference between these, right? So when we say, a parameterization or the parameterization, we're talking about the vector valued function. When we talk about the curve, we're talking about a picture, right? So the first and most important note I want to make here is any given curve generally has many parameterizations. So every curve has many parameterizations. Now, I'm going to abbreviate the word parameterizations with just params constantly because it makes it a bit easier. So let me give you an example. Go back to the circle. So this curve, we draw it in blue again. So I'm not going to give it a direction or anything like that, just make it a full circle. This, let's say, has all of the following parameterizations. So we could do r of t, the first one we gave, right? This cosine t I plus sine t j for t between 0 and 2 pi. Or, right, here's a different parameterization. That draws exactly the same picture. So now t goes between 0 and pi, but the 2t that's inside the cosine and the sine sort of double it and draw the same picture, right? So different parameterizations, same curve, right? And you could do this endlessly, right? You could do cosine of 4t, right? You could just keep playing. And I'm not suggesting that we're going to be doing this. all I want to do is make sure that we're clear of the distinction between those. Okay. So all three of these and more, you could go forever and ever and ever, are different parameterizations. But there's just one curve in this case, right? So in other words, a parameterization will give you a curve, but a curve will have many parameterizations. So just keep those terms in mind, because there'll be many times in the course later when I'll make a statement like, hey, I'll give you a curve, I'll describe it somehow. And I'll say like, what's a parameterization of that? And you'll need to come up with the R, right? So just to sort of a closing thing for a number one, I could say a goal, sort of a goal, is given a curve. Somehow it could be a picture, some sort of description, as we'll see. Can you come up with a nice parameterization? And for right now, you don't need to, like, the word nice is very flexible. It's just like, can you come up with a vector valued function that draws the curve? And so just so we're clear about the difference between those. So that's the first thing, curves versus parameterizations. Keep that in mind. So second definition I want to give is definition of the word closed. So let me clear the screen, talk about what it means to have a closed curve versus not a closed curve. So we'll say two. Closed. I'll say closed versus non-closed. I won't say curves or not curves just yet. I'll keep those separate. So, definition. So what's going to happen for the next couple of definitions, I'm going to give a definition that applies to a parameterization, and then we're going to extend it to apply to a curve, and hopefully it'll make it clear what the distinction is. Hopefully this example, this particular definition, closed versus non-closed, will help clarify that. So a parameterization, R of t, for t between a and b. So this is for a parameterization that has endpoints. In other words, it has restrictions on t, is closed. So it's an odd word, but it's closed if two things are true. Right? If the following, a, R of a equals R of b. So what this means is it begins where it ends. Start equals finish. Like the start point and the finish point. And b, it does not cross itself infinitely many times. This is somewhat of an esoteric requirement. It's a little more nuanced than that, but in order to talk about what the formal definition for B is, the formal phrasing, we need a lot more math. So this is sufficient for us. It might seem a bit weird. It will almost never happen, but I just want to make a point just so that you see. Let me give you two examples. So the circle, right? This very first one. It's a great example. Oops, sign right there. If you plot this thing, right, it makes full circle. Now it starts and it begins at the same point, right, on the right-hand side. So it does touch itself one time. Right? So two things are true. Right? It begins where it ends. So this point right here, this is R of 0, and it's the same as R of 2 pi. They're both at the point 1i, or vector if you like, 0j. Now, so it starts where it begins. Right? In that sense, it's closed. Now, does it cross itself? Well, it does touch itself at the beginning, at the end, right? It touches itself right there. But that's one time. And that's okay, right? Not a problem. Now, consider if I did something like this. I'm going to stick with the same exact function, vector value function, but I'm going to go 0 to 4 pi. So the picture is exactly the same. But as I draw it, think about what happens. When we start, it begins right here. Then it does a full circle, and then it runs over the same circle again. So it does start where it ends, right? Like, it's still absolutely true that it begins where it ends. But it runs over itself a full time. That's infinitely many times, like a full circle. So it runs over itself at infinitely many points. So this guy up here, he's closed. This one is not closed because it is not allowed to do that. It's not allowed to run, touch itself, contact itself, cross itself. Cross is a bad word. Touch is a better word. Now what's not closed? Right? And then, of course, an example like r of t equals, let's go back to the parabola, for example. This one, parabola we've seen a couple times. This one, if you plug in the endpoints, goes from 0, 0 to 2, 4. All right, the start point and the end point are different. This is not equal. So it's not closed. So now, definition that goes with this. It's because all these definitions are about a parameterization. Right, back up here, there's all statements about R. So what we'll then say is we'll say that a curve is closed if it has a parameterization. In other words, if we can come up with a parameterization which is closed. So, for example, if I started the discussion by giving you the circle, right, not the, let's say a circle, let's say circle of radius 2, just for something different. That's a terrible circle of radius 2. It's all sort of wonky. Right, if I just drew the circle and I didn't give you the vector valued function, and I said to you, is it closed? Right? You could respond, yes, it's closed. And if I said why, you could say, because here is the parameterization which does the job. Does a full circle, starts and ends at the same point. Now, you can also come up with parameterizations which do a terrible job. You can come up with parameterizations which go multiple times. But the argument is it's closed if you can come up with one that works. And so we came up with one, it's closed, done. Right? Now, look at something like this. If I were to draw like a line segment, it's like a straight line segment, or even a bendy line segment, like this. That is not closed, right? There is no way, like, even if you could come up with some crazy function. The trouble is that, like, you might think that you could start it and end it at the same point and just backtrack, but you're not allowed to backtrack because as soon as you start backtracking, the curve will touch itself infinitely many times. So this is no parameterization will do the job. We need to backtrack, right? In other words, for the start to equal the end, we need to backtrack. But we can't. But this would result in the parameterization touching itself infinitely many times. So in an informal sense, a curve is closed if it begins where it ends. That's a loose definition. But a more formal definition is these requirements about not touching itself too many times and being more formal with respect to the parameterization. But basically, intuitively, it forms a loop. Now, let me just draw one more example in here just to give that in. Let me cram it over on the edge. I'm just going to draw a very simple picture. Curve like a figure eight or an infinity sign. Even though it's not clear to us what the parameterization is, you might remember curves like this from Calc 2. I'm not going to dig into them. We don't need to worry about them. The idea intuitively is like, look, it forms a loop of sorts. It does cross itself once in the middle. It also touches itself where it begins and ends. That's okay. That is closed. All right, this second one was not closed. So that's closed versus not closed. So take a second, digest that. Then we'll move on to the other definition, which is smooth. We'll say smooth versus, well, let's be careful. It's not for smooth / piecewise smooth. So one warning about this is there's a formal mathematical definition of smooth, and this is not it. Right? So this is sort of a baby version of the word smooth. And so if you go and you study geometry or something a little more technical, like upper level math, you're going to run into a more formal definition of smooth, which is different than this. So just keep this definition for this class, and it's sufficient. It's used in some lower level courses to mean this, but it's not entirely accurate in a grand mathematical scheme. So let me sort of do this the same way we did before. So let me start with the parameterization. The parameterization R of t is smooth. So here's the definition. So basically, that the derivative of R has to exist everywhere R does. Oops, everywhere that R itself exists. That derivative needs to be continuous. And the derivative, this is going to sound weird, it's a mouthful. The derivative cannot be 0 except at the endpoints if there are endpoints. Well, like when I say endpoints, I mean start and endpoints. If it has start and endpoints. Let's say start and end. So remember, the derivative indicates the velocity. So a way of thinking about this, sort of a fun exercise, is it's like your ideal drive to school. Is you get in your car and your velocity is 0. That's okay. You start driving. Your velocity is never 0 the whole way because you hit all green lights, you blew through the stop signs, maybe irresponsibly, and you get to school and you stop your car and then your velocity is 0 again. That's like ideal. That's smooth. Right? Now, let me I'm going to sort of give a couple definitions together, and then we'll do an example. So parameterization R of t is piecewise smooth. So it's piecewise smooth if the interval on which it's defined, like the t values, we'll say may be broken up into subintervals on which it's smooth. And then along with that, actually, I'll say something about the curve in a second, right? And then it's neither of these if neither is true. We'll see an example of that in a second. So let me start with a really, really simple example. Let's consider this vector value function, this parameterization. We'll do something like t squared minus 4ti plus sine of pi over 4tj. This isn't completely trivial. T between 0 and 2. Right? So this function is defined everywhere for t between 0 and 2. So if we take the derivative, we get 2t minus 4i. And then chain rule kicks in. Now, this function is defined everywhere t is, because this function is defined everywhere. Right? So that's one thing to keep in mind. Actually, let me make a few comments here. This is defined everywhere that R is, because it's defined everywhere. Now, notice it's continuous because all the functions it's made up of are continuous. Polynomials, etc. But here's the thing. If we look at when it's 0, right? So when is this function the 0 vector? Right, if anywhere. Right, so you go, well, the first one is 0 when t equals 2, because 2 times 2 minus 4 equals 0, right? So 2t minus 4 equals 0 when t equals 2. And if you plug t equals 2 into the second one, you also get 0, because you get the cosine of pi over 2, which is 0, so you also get it there. So what that says is that the derivative at 2 is 0. And we go, but that's okay, because that's an endpoint, right? The function is defined on 0, 2. Because let's say t equals 2 is an endpoint. And again, just to clarify what we mean by that, when we say an endpoint, we mean it's an endpoint of this interval on which we're interested. Now, keep in mind, t equals 2 is the only place that this is the 0 vector, because 2t minus 4, the I component, is never 0 anywhere else. So if you're going to get the 0 vector, it must be t equals 2, and that works for both the I and the j. So everything's good. So here, again, just to clarify, it's not 0 bar anywhere else. So it's smooth. Now, suppose we did the same R, but we're going to change the interval. Right? Let's say 0 less than or equal to t less than or equal to 4. So now there's still a problem at 2. Right? Everything else is golden, but there's still a problem at t equals 2. And t equals 2 is no longer an endpoint. I say a problem, but still, maybe let's better say R of 2 equals 0. And t equals 2 is not an endpoint. Right? It's an interior point. This is not smooth. But then you might say, well, hold on a second. I can break this interval into 2 pieces. All right, so we can say, for example, R of t is smooth if t goes between 0 and 2, and it's smooth if t goes between 2 and 4. So in other words, it's smooth in pieces. It's got a smooth piece and another smooth piece. So therefore we say it's piecewise smooth. Now, this might make you wonder whether you could have a curve which is not either of these, because a common thought is like, well, look, if there are places where the derivative is 0, I just break them up there. And if there are a million places, I just break them up in a million places. What's the problem? So you might wonder, if I could give you an example of a curve which isn't piecewise smooth according to this definition. The answer is yes. So let me clear the screen, then I will I'll draw a picture of that, or I'll give you a function of that, and then I'll say a final note about being smooth and piecewise smooth for curves and not just parameterizations, and I'll draw a picture or two about that, and then we have one last formula to give. So take a look at this example. Really, really simple. T to the 1/3 I. That's it. No j's, no k's. T between 0 and 1. If you take the derivative, we get 1/3 t to the negative 2/3 I, which if we tidy it up a bit, is 1/3 t to the 2/3 I. Now here's a problem, right? We go, right, so r of t is defined at 0. But r prime of t is not. So that's it, right? So one requirement is you always have to have the derivative wherever you have the function. In this case, it doesn't matter how you break it up. Like 0 is a problem everywhere, right? So this is not smooth or piecewise smooth. It's a somewhat esoteric example, but just, we're not really going to encounter these, but it's just to mention this. Then last, before our final formula, is we say a curve, not spelled badly, a curve is smooth or piecewise smooth if it has a smooth, piecewise smooth parameterization. So we won't be doing this a lot, but just to give you an intuitive feeling, like basically we'll work with the parameterizations, but just to give you an intuitive feeling, generally a curve will not be smooth if it has like cusps or sharp angles. Right, so in other words, for example, if I were to draw a curve like this, that's fine. But if I were to draw a curve like this, that's not, right? Assuming that the things that look like angles are angles. So that's not allowed to be. Right? Now let's just be clear, right? The one on the left, this is smooth. The one on the right, this is piecewise smooth because I can snap it into 3 pieces. In which it's smooth, right? All 3 of those. So, last thing, then. Again, don't worry so much about the pictures for that last example. We won't really be dealing with those that much. So, last thing I want to give is a formula. This is the formula for the length of a curve. Now, let's actually be really clear. This is actually a definition of a length of a curve. So given a curve C with parameterization, C is just the name of the curve, just to give it a letter, with a parameterization R of t for t between A and B, not necessarily 0, So the length of C is given by the following formula. It's the integral from A to B of the magnitude of the derivative of R. Now, if you stop and you think about this, this seems like a mouthful, but it kind of makes sense. Right? Now, so I'm going to say two things about this, and then we'll do an example, and then we'll call it a section. So one is, it makes sense because R prime, the magnitude of R prime, is the speed. So you're actually integrating speed, and when you integrate speed, you get distance, right? Because intuitively in Calc 1, speed is the derivative of distance or of position in a one-dimensional sense. So it makes sense because we're integrating speed. The second thing is, in order to do this, in order to even integrate this, I have to have a pretty nice function, right? So it turns out that R must be piecewise smooth to do this. Now, this is not something you will ever need to check. Right? I'm only mentioning this as a matter of course, just so that we can sort of make a reference between this formula and the work we just did, that if R is not piecewise smooth, we could end up with a function which has no derivative, or the derivative is not continuous. Maybe we get something that we can't integrate, etc. There are some technical details that we're glossing over here. But to make the point is, if we have a piecewise smooth curve, we can definitely do this. We can definitely calculate a length. So, then we just close with a simple example. Let me go back from blue. I'll do a really, really simple one. But we'll do a line segment. 2ti plus 3t plus 2j, t between 0 and 7. So this is just to see the application of a problem, of the formula. To find the length, we integrate from 0 to 7. We take the magnitude of the derivative. This is the derivative of R. Right, so don't forget, the biggest mistake that students make often is to forget to take the derivative. They accidentally put the R in here and then it doesn't work out so nice. Right? So keep in mind when we integrate, this is not a vector valued function because we're taking a magnitude. So this is the square root of 4 plus 9. This is the square root of 13. It's a really easy integral. So we get the square root of 13t. So we get 7 root 13. Sorry, that's really badly written right there. Now, naturally, the integrals can be harder than this, right? But I don't want this to be an exercise in integration right here. I just wanted to point out, like, this is something new that we can do with a parameterization. The R of t, we can take the derivative, take the magnitude, integrate that to get the length. So, that is the end of that section. There's one more section in chapter 12 to go. That'll be 12.5.